What if I told you that right now, as you're watching this video, there are parts of the universe racing away from you faster than the speed of light, not breaking the laws of physics, not violating Einstein's sacred speed limit, but actually, legitimately, moving faster than light relative to you. And here's the kicker. This isn't some fringe theory. This is mainstream cosmology. This is accepted science. And if that doesn't immediately break your brain, here's the follow-up. If something is moving faster than light away from you, you can never, ever see it. It's gone from your universe forever. It might as well not exist for you. But wait, didn't we learn in school that nothing can go faster than light? Didn't Einstein prove this? How can something be moving faster than light and still follow the rules? And more importantly, what does this mean about reality itself? What exists beyond that light speed barrier that we can never touch, never see, ever know? Today, we're going on a journey that will fundamentally change how you understand reality. We're going to explore what happens beyond the speed of light, and I promise you, the answer is far stranger, far more beautiful, and far more unsettling than you ever imagined. Before we dive in, do me a favor. Hit that like button, smash subscribe, and drop a comment telling me where you're watching from and what time it is for you right now. I'm genuinely curious to see how global this community is. Are you in Tokyo at 3 a.m.? London during lunch? New York winding down your evening? Let me know. This topic transcends borders, and I want to see how far we're reaching across this planet that's all trapped together inside the same light speed bubble. Let's start with what you think you know, and then I'm going to systematically dismantle it and rebuild something far more interesting. You've probably heard that nothing can travel faster than the speed of light. This comes from Einstein's special theory of relativity, published in 1905. The speed of light in a vacuum, approximately 299,792,458 meters per second, or about 186,282 miles per second. We usually just call it c for convenience. Einstein's revolutionary insight was that this speed isn't just really fast. It's a fundamental speed limit baked into the fabric of spacetime itself. But here's your first mind-bending twist. Einstein never said nothing can move faster than light. What he actually said was that nothing with mass can accelerate to the speed of light, and that no information can travel faster than light through space. These might sound like the same thing, but they're not. And that tiny distinction opens up a universe of possibilities that most people never consider. Think of it like this. Imagine spacetime as a vast ocean. Einstein's rule says that no boat can sail through the water faster than a certain speed. But what if the ocean itself is moving? What if currents can flow faster than boats can sail? What if whirlpools can spin faster than any boat could navigate? The boat still obeys the speed limit relative to the water around it, but the water itself isn't bound by those same rules. This is where things get wild. Space itself, the actual fabric of the universe, can expand faster than light. It is expanding faster than light right now. And when space expands, it carries galaxies along with it like boats on a current. Those galaxies aren't moving through space faster than light. They're moving with space. And Einstein's equations have absolutely no problem with this. The first person to really understand this was Edwin Hubble. In 1929, Hubble made one of the most important discoveries in human history. He was observing distant galaxies from the Mount Wilson Observatory in California, using what was then the world's largest telescope. He noticed something bizarre. The light from these galaxies was shifted toward the red end of the spectrum. This redshift, as it's called, happens when the source of light is moving away from you, stretching out the light waves like a siren moving away from you drops in pitch. But here's what made Hubble's discovery revolutionary. The farther away a galaxy was, the faster it appeared to be moving away. This wasn't random motion. This was systematic. The universe itself was expanding, and the expansion meant that distant objects were receding from us at speeds proportional to their distance. Hubble calculated what we now call the Hubble constant, a number that describes how fast the universe is expanding. Now, do the math on this. If expansion speed increases with distance, then at some distance far enough away, objects must be receding faster than light. And they are. The current observable universe has a radius of about 46.5 billion light years. But the universe is only about 13.8 billion years old. How can we see light from something 46.5 billion light years away if the universe is only 13.8 billion years old? Because space itself has been expanding the entire time that light has been traveling toward us. Those distant galaxies were much closer when they emitted the light we're seeing now, but they've since been carried away by the expansion of space itself. Here's where your brain should start tingling. There's a distance called the cosmological event horizon, currently about 16 billion light years away. Any galaxy beyond that distance is receding from us faster than light due to the expansion of space. Any light they emit right now will never reach us, ever. Not in a billion years. Not in a trillion years. Not ever. Those galaxies are causally disconnected from us. They exist, but they might as well be in a different universe entirely. But I'm getting ahead of myself. Before we can really understand what exists beyond the light barrier, we need to understand why the light barrier exists in the first place. And trust me, the reason is far stranger then. It's just the speed limit of the universe. Why is the speed of light the speed limit? Not what is the speed limit, but WH. Why is it the speed limit? What makes 299,792,458 meters per second so special? Here's what will blow your mind. The speed of light isn't really about light at all. Light just happens to travel at this speed because photons have no mass. The speed limit we're talking about is actually the speed of causality itself. It's the speed at which cause and effect can propagate through the universe. It's the speed of reality updating. Let me explain this properly because it's crucial to everything that follows. In Einstein's special relativity, space and time aren't separate things. They're woven together into a four-dimensional fabric called spacetime. When you move through space, you're also moving through time. In fact, everything in the universe is always moving through spacetime at exactly the same speed, the speed of light, always, including you right now. Wait, you're thinking I'm sitting still. I'm not moving at the speed of light, but you are. You're just moving entirely through the time dimension and not at all through the space dimensions. See, there's a trade-off. The more you move through space, the less you move through time. This is time dilation, the famous effect where moving clocks run slower. Think of it like this. Imagine you have a car that always travels at exactly 60 miles per hour, no more, no less. But you can choose how much of that speed goes north and how much goes east. If you go entirely north, you're going 60 miles per hour north and 0 miles per hour east. If you go northeast at a 45-degree angle, you're going about 42 miles per hour north and 42 miles per hour east. The total speed is still 60 miles per hour. You've just divided it between two directions. Space-time works the same way. Everything always moves through space-time at c, the speed of light. If you're sitting still, all of that motion is through time. You're aging at the maximum rate. If you start moving through space, some of that motion gets redirected from the time dimension into space dimensions. You're now moving through time more slowly, which means you age more slowly. Time dilation isn't some weird side effect. It's a direct consequence of the geometry of spacetime. Now here's the crucial part. If you could somehow accelerate to the speed of light, all of your motion through spacetime would be in the space dimensions, and none would be in the time dimension. Time would stop for you. You wouldn't experience any time at all. This is why light itself doesn't experience time. From a photon's perspective, it's emitted and absorbed in the same instant, even if it travels across the entire universe. The journey takes no time from the photon's reference frame, and this is why nothing with mass can reach the speed of light. To do so would require all of your motion through spacetime to be redirected into space, leaving none for time. But mass creates a kind of drag in spacetime. The more mass something has, the more it resists acceleration. As you approach the speed of light, your relativistic mass increases, making it harder and harder to accelerate further. To actually reach the speed of light would require infinite energy. This was mathematically proven by Einstein in 1905, but it was experimentally verified thousands of times. Particle accelerators, like the Large Hadron Collider near Geneva, Switzerland, accelerate protons to 99.999991% of the speed of light. At those speeds, the protons have so much relativistic mass that they hit with the energy of mosquitoes, despite being subatomic particles. But no matter how much more energy you pump in, you can never quite get them to 100% of light speed. You just keep getting closer and closer. 99.999999999999999999%, but never quite there. But here's where things get interesting, and this is your second major revelation. Just because nothing can accelerate to light speed through space doesn't mean nothing can already be going faster than light in other ways. Quantum entanglement is the first hint of this. When two particles are entangled, a measurement on one instantly affects the other, no matter how far apart they are. Albert Einstein, working with Boris Podolsky and Nathan Rosen in 1935, called this spooky action at a distance and thought it meant quantum mechanics must be incomplete. How could two particles, separated by vast distances, instantly affect each other? Wouldn't that require information to travel faster than light? It took until 1964 for physicist John Stuart Bell to prove that quantum entanglement was real and unavoidable. And it wasn't until the 1980s that experiments by Alain Aspect in France definitively proved that entanglement really does work instantaneously, faster than any signal traveling at light speed could explain. Aspect won the Nobel Prize in Physics in 2022 for this work. But here's the twist. No information actually travels between the entangled particles. The correlation is perfect and instantaneous, but you can't use it to send a message faster than light. It's like having two coins that always land on opposite faces. If you flip one in New York and it lands heads, you instantly know the one in Tokyo landed tails. But you can't control which way your coin lands, so you can't encode a message. The correlation is faster than light, but causality, the ability to make something happen somewhere else, is still limited to light speed. This brings us to a crucial distinction that most people miss. There's a difference between something moving faster than light, something happening faster than light, and information traveling faster than light. These are not the same thing, and the universe treats them very differently. What happens beyond the speed of light isn't about breaking physics. It's about understanding what physics actually allows versus what we casually assume it forbids. Before we go further, let me ask you something that's going to seem random, but isn't. If you're watching this right now, what's the farthest thing you can see? If you're indoors, maybe it's a wall 20 feet away. If you're outside during the day, maybe it's a mountain on the horizon, miles away. If you're watching this at night, maybe it's stars that are light years distant. But here's the thing, that's not actually the farthest thing you can see. Right now, you are seeing the cosmic microwave background radiation. It's not visible to your eyes, but it's there, passing through your body every second. That radiation has been traveling toward you for 13.8 billion years, since just 380,000 years after the Big Bang. It's the farthest thing it's possible to see, the edge of the observable universe. And beyond that edge, beyond that cosmic horizon, that's where we're going next. Make sure you're subscribed because what comes next will challenge everything you think you understand about existence itself. We're about to explore the cosmic event horizon, the boundary beyond which the laws of physics allow things to exist that can never, ever interact with us. Ready? Let's go. Imagine you're standing on a beach and you're watching a boat sail away. At first, you can see the whole boat clearly. As it gets farther away, you see less detail, but you can still see it. Eventually, it disappears over the horizon. But here's the thing. The boat didn't cease to exist. It's still there. It's just beyond your ability to see it because of the curvature of the Earth. The cosmic event horizon works similarly, but with a crucial difference. The boat could, in principle, turn around and come back. Things beyond the cosmic event horizon cannot. They're gone forever, and not because they've been destroyed, but because space itself is expanding so rapidly between us and them that even light cannot bridge the gap. Let me make this concrete. Right now, in 2025, the cosmic event horizon is approximately 16 billion light-years away. Any galaxy beyond that distance is receding from us faster than the speed of light due to cosmic expansion. If an alien civilization on a planet in one of those galaxies pointed a laser at Earth right now, that light would start traveling toward us at the speed of light. But space itself is expanding between us and them faster than the light can traverse it. It's like a person on a treadmill. They're running forward, but the treadmill is pulling them backward faster than they can run. They make no net progress. That light will travel for trillions upon trillions of years, forever trying to reach us, and it will never arrive. It will get closer for a while as the expansion rate varies, but ultimately, the accelerating expansion of the universe means it will fall farther and farther behind until the photons are stretched, so thin by cosmic expansion that they lose all their energy and become undetectable background radiation. This raises an absolutely profound question. If something exists but can never, ever affect you in any way, does it exist for you? Philosophers call this a question of phenomenology, the study of experience and consciousness. If an event occurs in a part of the universe forever beyond your cosmic horizon, and no information about it can ever reach you or affect you in any way, is that event part of your reality? Or is reality defined by what you can, in principle, interact with? This isn't just philosophical navel-gazing. This has real implications for how we understand the universe. According to our best measurements, the observable universe contains about 2 trillion galaxies. But the universe beyond our cosmic horizon? It might be infinite. It probably is infinite. If inflation theory is correct, and all evidence suggests it is, then the universe is vastly, incomprehensibly larger than what we can observe. The observable universe might be to the total universe what a single atom is to the entire Earth, or smaller, or infinitely smaller. Let me introduce you to Alan Guth, the physicist who developed inflation theory in 1980 while working at MIT. Guth realized that if the early universe underwent a brief period of exponential expansion, a fraction of a second after the Big Bang, it would solve several puzzling problems in cosmology. But it also means that the universe is far, far larger than what we can observe. Think about what this means. Somewhere beyond your cosmic horizon, there might be an exact duplicate of you. In an infinite universe with a finite number of ways to arrange matter, every possible configuration must occur, not once, but infinitely many times. There's a version of you that made every possible different choice. There's a version of you that's living your dream life. There's a version of you that made opposite choices at every turn. They exist right now, living their lives, but they might as well be in a completely different universe, because you can never, ever interact with them. But here's where things get even stranger. The cosmic event horizon isn't static. It's changing as the universe expands and as the expansion rate changes. Due to dark energy, the mysterious force causing the universe's expansion to accelerate, the cosmic event horizon is actually getting closer to us in a sense. Galaxies that are currently within our event horizon, that we could in principle reach if we left right now traveling at near light speed, are slipping beyond the horizon as the universe expands. In fact, the vast majority of galaxies we can currently see are already beyond the cosmic event horizon. We can see them because the light left them billions of years ago when they were closer and the expansion was slower. But if we tried to travel to them now, even at the speed of light, we could never reach them. They've already slipped beyond the point of no return. Lawrence Krauss, a cosmologist at Arizona State University, calculated in 2000 that if dark energy continues to behave as it currently does, then, in about 150 billion years, every galaxy outside our local group will have slipped beyond the cosmic event horizon. Future astronomers looking at the sky won't see the vast cosmos full of galaxies that we see. They'll see a much emptier universe. All evidence of cosmic expansion will have literally left the observable universe. They'll look up and see a handful of nearby galaxies and assume that's the entire universe. In other words, the cosmos is hiding itself from the future. Evidence of the Big Bang, of cosmic expansion, of the vast scale of the universe will eventually become unobservable. If we didn't exist right now, in this cosmic epoch where the evidence is still visible, would future civilizations ever discover the truth? Or would they be trapped in a smaller conception of reality, forever unable to discover what lies beyond because all evidence had slipped beyond the event horizon? This brings up an unsettling possibility. What evidence has already slipped beyond our cosmic horizon? What aspects of reality existed in the early universe, left evidence that has now expanded beyond our ability to observe it? Are we already living in a cosmos that's hiding profound truths from us simply because the universe has been expanding for 13.8 billion years? What happens beyond the speed of light isn't just a question about physics. It's a question about the nature of knowledge itself. How can we understand reality when large parts of reality are forever beyond our ability to observe? Now let's talk about something that sounds like pure science fiction, but is actually serious physics. Tachyons. These are hypothetical particles that always travel faster than light. Not particles that accelerated past light speed, but particles that were born going faster than light and can never slow down to light speed. In 1967, physicist Gerald Feinberg, working at Columbia University, published a paper asking a simple question. What if there are particles that exist on the other side of the light speed barrier? Regular matter, which we call tachyons, can never reach light speed from below. Light itself, made of massless photons, travels at exactly light speed. But what if there's a third category? Particles that always travel faster than light. The mathematics of relativity don't actually forbid this. They just forbid crossing the light barrier. If something has imaginary mass, yes, that's a technical term involving the square root of negative numbers, then the equations of relativity require it to travel faster than light. It can never slow down to light speed, just as we can never speed up to light speed. The light barrier would work both ways. Now, before you get too excited, we've never detected a tachyon. Despite decades of searching, there's no experimental evidence they exist. But the fact that they're mathematically possible opens up fascinating questions about what reality could be like. If tachyons exist, they would have genuinely bizarre properties. For one, they would travel backward in time from some reference frames. This doesn't mean they're time machines in the traditional sense, but rather that the sequence of cause and effect would appear reversed depending on how you're moving relative to the tachyon. Think of it like this. Imagine you see lightning flash and then hear thunder. The light and sound both left the lightning bolt simultaneously, but light travels faster than sound, so you see the flash first and hear the thunder later. Now imagine something travels so fast that it arrives before the light from its origin point. From your perspective, you'd see the effect before the cause. You'd see the tachyon arrive, and only later would you see the light from where it originated. This creates all sorts of paradoxes. If you could control tachyons and send information faster than light, you could exploit relativity to send messages into your own past. You could create causal loops where effects precede their causes. This is often called the tachyonic antitelephone, a thought experiment showing that faster-than-light communication would enable time travel communication. Most physicists think this means tachyons probably don't exist, or if they do, they can't be used to transmit information. The universe seems very careful about maintaining causality, the principle that causes precede effects. Every time we've found something that seems to violate this principle, closer examination reveals it actually doesn't. But here's where it gets interesting. Certain quantum field theories predict tachyonic fields as mathematical possibilities. String theory, the leading candidate for a theory of quantum gravity, includes tachyonic states in some of its formulations. These aren't stable particles you could detect, but rather unstable fields that quickly decay into normal matter. The presence of tachyonic fields in the mathematics often indicates that the system is in an unstable state and wants to transition to a different configuration. Some cosmologists have even proposed that tachyonic fields might explain dark energy, the mysterious force accelerating cosmic expansion. In this model, a tachyonic field fills space, causing it to expand at an accelerating rate. The field is unstable, always trying to decay, and that inherent instability manifests as the accelerating expansion we observe. Whether or not actual faster-than-light particles exist, the fact that the mathematics of relativity allows for them tells us something profound. The speed of light barrier isn't a wall that separates allowed from forbiddens. It's more like a barrier separating two different realms of possibility, each internally consistent, but unable to pass objects between them. This leads to a mind-bending possibility. What if there are entire domains of the universe made of tachyonic matter? Regions where everything travels faster than light, where causality runs backward from our perspective, where time and space behave in ways completely alien to our experience. These regions would be forever undetectable to us, because nothing slower than light could exist there, just as nothing faster than light can exist here. We'd be separated not by distance, but by this fundamental barrier in the structure of spacetime itself. It's like imagining a universe where everyone is swimming underwater and you're trying to explain what it's like to walk on dry land. They could understand the mathematics of your description, but they could never visit your world or you theirs. You're separated by a fundamental change in the medium of existence itself. Let me pause here and ask you something. How many times in your life have you had a moment where your understanding of reality fundamentally shifted, where you realized something you thought was true was actually just a simplification or even completely wrong? That's what we're doing here. We're not just learning facts about physics. We're restructuring how you understand the very fabric of existence. And we're only halfway through this journey. If you're finding value in this deep dive, hit that like button. Share this with someone who loves thinking about the nature of reality. And drop a comment. What aspect of this topic has blown your mind the most so far? The cosmic event horizon? The possibility of tachyons? The fact that space itself can expand faster than light? And seriously, if you haven't subscribed yet, what are you waiting for? Click that button. Because what's coming next is going to tie all of this together in ways you're not expecting. We're about to talk about wormholes, warp drives, and whether the universe actually has a speed limit at all. Let's talk about cheating. Not breaking the rules, but finding loopholes. Can you get from point A to point B faster than light without actually traveling faster than light? The answer, surprisingly, is maybe. This brings us to wormholes, technically called Einstein-Rosen bridges, after Albert Einstein and Nathan Rosen, who first described them mathematically in 1935. A wormhole is a shortcut through spacetime. Imagine the universe as a flat sheet of paper. Los Angeles and Tokyo are on opposite sides. To travel between them across the surface takes time. But what if you could fold the paper so the two cities touch, poke a hole through, and step from one to the other? You wouldn't be traveling faster than light through space. You'd be taking a shortcut through a higher dimension. The mathematics of general relativity absolutely allow for wormholes. They're legitimate solutions to Einstein's equations. But there's a catch, and it's a big one. To hold a wormhole open, you need exotic matter with negative energy density. This isn't antimatter, which is well understood and has been created in labs. This is something much stranger. Matter that has less than zero energy, that pushes instead of pulls, that anti-gravitates. We've never seen macroscopic exotic matter, but quantum mechanics does allow for negative energy densities on tiny scales. The Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948, shows that the vacuum of space has fluctuating energy, and you can arrange metal plates to create a region with less than the average vacuum energy, effectively negative energy density. It's been measured. It's real, but it's incredibly weak. In 1988, physicist Kip Thorne at Caltech and his colleagues published a serious scientific paper about traversable wormholes, ones that a human could actually travel through. Thorne won the Nobel Prize in 2017 for his work on gravitational waves, so he's not some crackpot. His team showed that if you could somehow gather enough exotic matter, you could, in theory, create a stable wormhole. Here's what's fascinating. If a wormhole connects 2 points in space, and you accelerate one end of the wormhole to near light speed while keeping the other end stationary, time dilation means the two ends age at different rates. You'd create a time machine. You could enter the moving end in your present and exit the stationary end in your past. Of course, you could only travel back to the moment the wormhole was created. You couldn't go back and kill your grandfather or prevent your own birth. But you could create closed time-like curves, loops in time where events can influence their own past. The mathematics allows it. Physics doesn't forbid it. But we've never seen any evidence it actually happens. This raises a fascinating question explored by physicist Stephen Hawking. Why don't we see time travelers from the future? If time travel is possible, shouldn't people from the future come back and visit us? Hawking proposed what he called the chronology protection conjecture, that the laws of physics somehow prevent time travel, even though the mathematics allows it. Maybe quantum effects destroy any wormhole that tries to become a time machine. Maybe the universe has some mechanism we don't understand that enforces causality. But here's where it gets even more interesting. In 1994, physicist Miguel Alcubierre, working at the University of Wales, published a paper describing what's now called the Alcubierre drive. It's a theoretical method of faster-than-light travel that doesn't violate relativity. Instead of moving through space faster than light, you compress space in front of your ship and expand it behind you, creating a wave that carries you forward. The ship itself isn't moving through its local space faster than light. It's surfing on a wave of compressed and expanded spacetime. Think of it like a treadmill in reverse. You're standing still on the belt, but the belt is moving underneath you, carrying you forward. Relative to the room, you're moving, but relative to the belt, you're stationary. The Alcubierre drive does the same thing with spacetime itself. The catch? It requires exotic matter with negative energy density, a lot of it. The original calculations suggested you'd need more negative energy than the positive energy contained in the entire observable universe. That's clearly impossible. But subsequent refinements by physicist Harold White at NASA in 2012 suggested that with the right configuration, you might only need a few hundred kilograms of exotic matter. Still impossible with current technology, but not physically absurd. What's remarkable is that NASA took this seriously enough to fund a research team to study it. The EagleWorks laboratory at Johnson Space Center in Houston spent years investigating whether any aspect of the Alcubierre drive might be feasible. They didn't build a warp drive, obviously, but the fact that NASA thought it was worth studying tells you this isn't pseudoscience. This is serious theoretical physics exploring the boundaries of what the universe allows. Here's the thing that should blow your mind. Both wormholes and warp drives rely on manipulating the geometry of spacetime itself. They're not about going faster through space. They're about changing what space itself is doing. And Einstein's general relativity, the theory that describes gravity as curved spacetime, explicitly allows for this kind of manipulation if you have the right kind of matter and energy. So what exists beyond the speed of light? Maybe nothing goes faster than light through space. But maybe space itself can be warped, folded, compressed, and expanded in ways that effectively allow faster than light travel without violating the underlying physics. The universe might have loopholes built into its fundamental structure. The question isn't, can we break the light barrier? The question is, can we find a clever way around it that the universe permits? Now we're going to dive into the rabbit hole that is quantum mechanics. And I need you to buckle up, because this is where things get truly strange. What we've talked about so far is relativistic physics, the physics of the very fast. Now we're going to talk about quantum physics, the physics of the very small. And where these two theories meet, reality itself seems to break down. In quantum mechanics, particles don't have definite positions or velocities until you measure them. Instead, they exist in what's called a superposition, a sort of cloud of probability spread across space. The particle is, in a very real sense, in multiple places at once until you observe it. The act of observation causes the wave function to collapse, forcing the particle to choose a specific position. Here's where it connects to faster-than-light phenomena. When a wave function collapses, it happens instantaneously across all of space. If an electron's wave function is spread across a room, and you measure it on one side, the probability instantly goes to zero on the other side. A wave function collapse happens faster than light. It's not bounded by the light speed limit at all. This bothered Einstein so much that he spent decades arguing that quantum mechanics must be incomplete. In 1935, he published the famous EPR paradox paper with Podolsky and Rosen, arguing that if quantum mechanics were correct, you'd have spooky action at a distance, instantaneous influences across arbitrary distances. Einstein thought this was absurd, and therefore quantum mechanics must be missing something. But here's the thing, Einstein was wrong. Quantum mechanics really does have instantaneous influences. The experiments I mentioned earlier by Alling Aspect proved it definitively. The collapse of the wave function really is instantaneous, faster than light, across any distance. And this is crucial, you can't use this to transmit information faster than light. The result of a quantum measurement is random. You can't control it. So even though the collapse is instantaneous, you can't encode a message in it. Causality is preserved. You can't make something happen somewhere else, faster than light. You can only observe correlations that were set up in advance. It's like having two magic coins that always land on opposite sides. No matter how far apart you take them, when you flip one and it lands heads, the other is guaranteed to land tails. The correlation is instantaneous, but you can't control which way your coin lands, so you can't send a message using this correlation. The other person just sees a random sequence of heads and tails. Only when you compare notes later, at speeds limited by light, do you discover the correlation. But here's where minds start melting. Some interpretations of quantum mechanics suggest that wave function collapse isn't a real physical process at all. In the many worlds interpretation, proposed by Hugh Everett in 1957, while he was a graduate student at Princeton, the wave function never collapses. Instead, every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. When you measure that electron, the universe branches into one version where you found it on the left and another version where you found it on the right. Both versions are equally real. You just happen to experience one of them. In many worlds, there's no faster-than-light wave function collapse because there's no collapse at all. The wave function is the fundamental reality, and it evolves smoothly and locally according to Stinger's equation. The apparent collapse is just your subjective experience of finding yourself in one branch of the universal wave function rather than another. If many worlds is correct, and there's significant debate about this among physicists, then every quantum measurement is branching reality into incomprehensibly vast numbers of parallel universes. Every possible outcome of every quantum event is happening in some branch. There's a branch where you made every different choice, a branch where dinosaurs never went extinct, a branch where humans never evolved. All of it equally real, all of it existing simultaneously in the structure of the universal wave function. But here's the kicker. These parallel branches can never communicate with each other. They're separated not by distance, but by something called decoherence, the quantum mechanical process that makes different branches of reality unable to interfere with each other. You can't send a message to the version of you in a parallel branch any more than you can send a message faster than light. The separation is absolute. So what exists beyond the speed of light? In many worlds, there exists an infinite multiverse of parallel realities, each causally disconnected from the others, separated by the fundamental structure of quantum mechanics. These worlds are beyond any barrier you could cross, even in principle, even with unlimited technology. They exist, but they're fundamentally unreachable. This connects back to our earlier discussion about the cosmic event horizon. Just as there are parts of our universe beyond our cosmic horizon that we can never interact with, there might be entire parallel universes beyond our quantum horizon that we can never interact with. Reality might be far vaster than even the observable universe, extending not just in space, but in possibility space, in the space of all possible quantum outcomes. I want to pause the heavy physics for a moment and talk about what this all means for you. You're sitting there, watching this video, living your life on a small planet orbiting an average star in an ordinary galaxy. And what we've just discussed is that most of reality is forever beyond your reach. Not because of technological limitations, but because of the fundamental structure of the universe itself. There are galaxies beyond your cosmic event horizon that you will never see, never visit, never know anything about. They exist, but they might as well be in a different universe entirely. If many worlds is correct, there are versions of you living different lives in parallel quantum branches, and you will never meet them, never communicate with them, never even know they're there. The speed of light isn't just a speed limit. It's a horizon that defines the boundary of your reality. But here's what I want you to understand. This isn't a tragedy. This is profound. Think about it. You exist in a universe so vast, so incomprehensibly large, that most of it is beyond anyone's ability to observe. The observable universe contains 2 trillion galaxies, each with hundreds of billions of stars. That's more stars than grains of sand on all of Earth's beaches. And that's just what we can see. Beyond our cosmic horizon, there might be infinitely more. You are one conscious being among potentially trillions upon trillions across the cosmos, each living your own life, having your own experiences, most of whom will never know the others exist. And yet you matter. Your experiences are real. Your choices have consequences. The fact that most of the universe is beyond your reach doesn't diminish the significance of the part you can touch. Think of it like this. Imagine you're born in a vast library with infinite books. You have a finite lifetime, so you can only read a tiny fraction of them. Does that make the books you do read meaningless? Of course not. If anything, it makes them more precious. You have to choose carefully which stories to engage with, which knowledge to pursue, which experiences to have, because you can't have them all. Your observable universe is like that. You have roughly 13.8 billion years of cosmic history to explore, 2 trillion galaxies to observe, and 1 precious lifetime to do it in. The fact that there's more beyond doesn't diminish this. It enriches it. It means you're part of something incomprehensibly vast. But let me make this even more personal. Let's talk about the speed of light in human terms. Light travels at 299,792 kilometers per second. That sounds incredibly fast, but in human terms, it's agonizingly slow. The nearest star to Earth, Proxima Centauri, is 4.24 light-years away. That means light from Proxima Centauri takes 4.24 years to reach us. When you look at Proxima Centauri, you're seeing it as it was 4.24 years ago. You're literally looking backward in time. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is about 2.5 million light-years away. When you look at Andromeda, you're seeing it as it was 2.5 million years ago, before humans existed. The light left Andromeda when our ancestors were still primitive hominids learning to use stone tools. That light has been traveling through empty space for 2.5 million years just to reach your eyes tonight. Now think about this. If there's an alien civilization in Andromeda with a powerful telescope looking at Earth right now, they're seeing Earth as it was 2.5 million years ago. They're seeing a planet with no cities, no agriculture, no human civilization at all. Just animals roaming a pristine world. As far as they can tell, Earth is uninhabited by intelligent life. If they sent us a message right now using radio waves, which travel at the speed of light, that message would take 2.5 million years to reach us. And our reply would take another 2.5 million years to reach them. A single round-trip communication would take 5 million years. Civilizations rise and fall in less time than that. By the time we received their message, they might be extinct. By the time they received our reply, we might be extinct. The speed of light doesn't just limit how fast we can travel. It limits how we can interact with the universe. It creates a fundamental isolation. Every civilization in the universe exists in its own local bubble, able to interact only with nearby neighbors, forever cut off from the vast majority of the cosmos. But here's where this becomes beautiful. It means your local interactions are what matter. The people in your life, the experiences you have, the community you're part of, these are your reality. The fact that there are trillions of other beings in other galaxies living their own lives doesn't diminish yours. If anything, it should make you appreciate what you have. You're here now, in this moment, aware of yourself and your surroundings. You have the ability to think, to feel, to experience wonder at the nature of reality. You're one of perhaps trillions of conscious beings scattered across the cosmos, each living in their own light-speed bubble, each having their own unique experience of existence. And you're connected to all of them through the shared structure of physics, through the same laws that govern your life and theirs, through the same fundamental reality that underlies everything. You're part of a cosmic family of conscious beings, most of whom you'll never meet, but all of whom share this strange, beautiful, bounded existence inside a universe that's simultaneously vast beyond comprehension and intimately knowable in your local experience. The speed of light doesn't trap you. It defines you. It creates the stage on which your life plays out. Without it, without this fundamental speed limit, causality wouldn't work. Cause and effect would be scrambled. Reality, as you know, it couldn't exist. The very structure that seems to limit you is actually what makes your existence possible. So when you look up at the night sky and think about all those galaxies beyond your reach, all those parallel quantum worlds you'll never visit, all that reality beyond the light barrier, don't feel small, feel connected. Feel part of something vast. Feel grateful that you get to experience even a tiny fraction of this infinite, beautiful, mysterious cosmos. You are the universe becoming aware of itself. You are matter and energy arranged in such a way that you can contemplate your own existence. And that's not diminished by the fact that most of the universe is beyond your reach. If anything, it's more profound because of it. Before we continue, I need you to do something for me. Look up from your screen. Look around you. Whatever you see, a ceiling, a sky, other people, objects in your room, remember that you're not seeing them as they are right now. You're seeing them as they were a tiny fraction of a second ago, the time it took light to travel from them to your eyes. Everything you've ever seen, you've seen in the past. You have never, not once in your entire life, seen the present moment. You've only seen the past. The present is always slightly beyond your reach, hidden behind the light speed delay. And that's just in your immediate surroundings. When you look at the stars, you're looking thousands of years into the past. When astronomers look at distant galaxies, they're looking billions of years into the past. The present moment of the universe, the now of everything that exists, is fundamentally unobservable. It's beyond the light barrier in a different sense, not in space, but in time. Isn't that wild? The present moment is beyond the speed of light. You literally cannot see it. You can only see the past. Drop a comment. Has this changed how you think about perception? About reality? About what now even means? And if you're still with me at this point, you're clearly someone who loves deep dives into reality. Subscribe if you haven't already, because we're about to go even deeper. We're going to talk about whether the speed of light has always been the same, whether it could change, and what it would mean if it did. Here's a question that should keep you up at night. Why is the speed of light the value it is? Why 299,792,458 meters per second and not some other number? Is there something special about this particular speed, or is it arbitrary, just the way things happen to turn out? This connects to one of the deepest questions in physics. Why do the fundamental constants of nature have the values they do? The speed of light, the charge of an electron, the strength of gravity, the mass of a proton, dozens of fundamental numbers that determine how the universe works. Change any of them even slightly, and the universe would be radically different. In 1999, physicist John Barrow at Cambridge University and João Magueo at Imperial College London proposed something radical. What if the speed of light wasn't constant? What if it was different in the early universe and changed over time? This is called variable speed of light theory, or VSL. Why would anyone propose this? Because it might solve some puzzles in cosmology. The horizon problem, for instance. The cosmic microwave background radiation is remarkably uniform across the entire sky. Different regions of space that are so far apart they couldn't have ever communicated with each other, even at light speed, have almost exactly the same temperature. How did they know to have the same temperature if they couldn't exchange information? Inflation theory solves this by proposing that space itself expanded exponentially in the first fraction of a second after the Big Bang, carrying distant regions apart faster than light. But VSL theory offers an alternative. What if light was much faster in the early universe? Then those regions could have communicated, synchronized their temperatures, and then the speed of light decreased to its current value. This is controversial. Most physicists think inflation is the better explanation. But VSL theory is still being investigated because it's not obviously wrong. The mathematics works. It's consistent with observations if you tune the parameters right. And it raises a profound possibility. The speed of light might not be a fundamental constant at all. It might be a feature of our particular cosmic epoch, something that was different in the past and might be different in the future. Some versions of string theory, the leading candidate for a theory of quantum gravity, predict that fundamental constants can vary across different regions of space or different cosmological epochs. In the landscape of string theory, there are something like 10,500 different possible vacuum states, each with different values for the fundamental constants. Our universe exists in one particular vacuum state, but others might have different physics entirely. If this is true, then the speed of light in our universe is like the temperature of Earth. It's not a fundamental property of reality. It's a local environmental condition that happens to be what it is here and now, but could be different elsewhere or elsewhere. But here's where this becomes unsettling. The fundamental constants appear to be fine-tuned for life. Change the speed of light by too much, and atoms don't form. Change the strength of gravity, and stars don't burn the right way to create heavy elements. Change the charge of the electron, and chemistry doesn't work. The universe seems to be balanced on a knife's edge, with parameters precisely set to allow for complexity, structure, and eventually life. This fine-tuning has led to several possible explanations. One is the anthropic principle. We observe these particular values because if they were different, we wouldn't exist to observe them. It's a selection effect. In a multiverse with different constants in different regions, we naturally find ourselves in a region where the constants permit our existence. Another explanation is that there's some deeper theory we don't know yet that predicts these values. Maybe they're not independent numbers that could have been anything. Maybe they're all related by some deeper mathematical structure. And once you understand that structure, you realize they had to be these values. A third explanation, uncomfortable to many scientists but philosophically viable, is that the universe was designed this way. Some intelligence or process set the constants to these precise values for some purpose. This isn't necessarily a religious claim. It could be that we're living in a simulation, that some advanced civilization created this universe and chose the parameters. Or it could be something else entirely that we can't even conceive of yet. But for our purposes, here's what matters. The speed of light is not just a random number. It's intimately connected to every other aspect of how reality works. It's woven into the fabric of spacetime, into the relationship between energy and matter, into the structure of causality itself. Changing the speed of light would ripple out and change everything. In 2001, a team led by John Webb at the University of New South Wales analyzed light from distant quasars and claimed they found evidence that the fine structure constant, a number related to the speed of light and the charge of the electron, might have been very slightly different billions of years ago. The evidence is controversial, and many physicists dispute it, but if true, it would mean the fundamental constants really do change over cosmic time. What would this mean? It would mean that the laws of physics aren't eternal and unchanging. They evolve. They have a history. The universe in the far future might have different physics than the universe today, just as the early universe had different physics than now. And if that's true, then what lies beyond the speed of light isn't just a spatial question. It's a temporal one. The physics of the far future or the distant past might be so different from today that phenomena impossible now might have been possible then, or might become possible later. The universe might go through phases, epochs where different rules apply, separated not just by time, but by fundamental changes in the constants of nature. You exist in a particular epoch where the speed of light has a particular value, where atoms are stable, where stars burn steadily for billions of years, where complex chemistry can create life. But this might be just one chapter in a much longer cosmic story, where different chapters have different physics, different possibilities, different realities. What exists beyond the speed of light? Maybe not just space beyond our horizon, but time beyond our epoch, versions of physics beyond our experience, realities beyond our comprehension. Now we need to talk about the most extreme objects in the universe, black holes. Because black holes take everything we've discussed about light speed, about event horizons, about causality, and push it to the absolute limit. A black hole is a region of spacetime where gravity is so strong that not even light can escape. The boundary where escape becomes impossible is called the event horizon, and it's a perfect one-way membrane. Things can fall in, but nothing can come out, ever. Here's what's crucial. The event horizon exists at the place where the escape velocity equals the speed of light. Outside the horizon, you could, in principle, escape if you had enough energy. Inside the horizon, you'd have to travel faster than light to escape, which is impossible. You're trapped, not by physical walls, but by the geometry of spacetime itself. This is eerily similar to the cosmic event horizon we discussed earlier. Both are boundaries beyond which causal contact becomes impossible. But there's a crucial difference. With the cosmic event horizon, things are moving away from you, faster than light due to expanding space. With a black hole event horizon, space-time itself is so curved that all paths lead inward. The future direction of time points toward the singularity at the center. Think about that for a moment. Once you cross the event horizon of a black hole, getting to the center isn't a spatial journey. It's a temporal one. The singularity isn't in front of you in space. It's in your future in time. You can no more avoid hitting the singularity than you can avoid tomorrow. It's not about flying the right direction. It's about the fact that all your possible futures lead to the same place. This was understood by physicist Roger Penrose in 1965 when he proved what's now called the Penrose singularity theorem. He showed that once an event horizon forms, a singularity is inevitable. General relativity predicts that you get a point of infinite density and infinite curvature, where the equations break down and we don't know what happens. But here's where things get truly bizarre. According to general relativity, if you fall into a large black hole, you won't notice anything special when you cross the event horizon. There's no barrier, no wall, no sudden change. You just keep falling. But to someone watching from outside, something very different happens. As you approach the event horizon, you appear to slow down. The light from you becomes more and more redshifted, stretched to longer wavelengths by the extreme gravity. You appear dimmer and dimmer, moving slower and slower, asymptotically approaching the horizon, but never quite reaching it. To the outside observer, you're frozen at the event horizon forever, fading to invisibility as your light becomes infinitely redshifted. But from your perspective, you fall through normally and continue toward the singularity. Two different observers see radically different things. This is an extreme case of relativity, where different reference frames genuinely experience different realities. Now here's the puzzle that's been bothering physicists since the 1970s. What happens to information that falls into a black hole? In 1974, Stephen Hawking discovered something shocking. Black holes aren't completely black. Quantum mechanical effects near the event horizon cause black holes to emit radiation, now called Hawking radiation. A black hole slowly evaporates, losing mass until eventually it disappears completely. But Hawking radiation is completely random, completely thermal. It contains no information about what fell into the black hole. If you threw an encyclopedia into a black hole and then waited for the black hole to evaporate, the Hawking radiation coming out would be random thermal photons with no trace of the information in the encyclopedia. This creates a paradox. Quantum mechanics says information cannot be destroyed. It's a fundamental principle. But black holes seem to destroy information. This is called the black hole information paradox, and it's one of the deepest unsolved problems in physics. Over the past few decades, the consensus has shifted toward the idea that information must somehow be preserved, though we don't fully understand how. Perhaps it's encoded in subtle correlations in the Hawking radiation that were too crude to detect. Perhaps it's stored on the event horizon itself in some kind of two-dimensional holographic encoding. Perhaps black holes don't fully evaporate, but leave behind remnants containing all the information. This brings us to one of the most mind-bending ideas in modern physics, the holographic principle. Proposed by Gerard T. Hooft in 1993 and given mathematical form by Leonard Susskind in 1995. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that space. Imagine a room. Common sense says the amount of information in the room depends on its volume, on how many particles are inside. But the holographic principle says it actually depends on the surface area of the walls. The three-dimensional interior is in some sense a projection of information encoded on the two-dimensional boundary. This sounds like science fiction, but it emerges naturally from studying black holes. The amount of entropy, which is essentially information, in a black hole is proportional not to its volume, but to the surface area of its event horizon. This was proven by Jacob Bekenstein in 1973 and refined by Hawking. The formula is simple. The entropy is proportional to the area divided by the Planck length squared. If this is true for black holes, maybe it's true for the universe as a whole. Maybe everything you experience, all of three-dimensional space, is actually information encoded on a distant two-dimensional boundary. You're like a character in a hologram, thinking you exist in 3 dimensions, not realizing you're actually a pattern on a surface. This connects to what exists beyond the speed of light in a profound way. Maybe what's beyond the cosmic event horizon isn't out there at all. Maybe it's encoded right here, in the structure of spacetime itself, in ways we can't directly perceive. The separation isn't spatial, but informational. Black holes show us that reality is far stranger than our intuition suggests. Event horizons create boundaries where our normal understanding breaks down. Inside a black hole, space and time swap roles. What was a spatial dimension becomes temporal, and you can no more avoid moving toward the singularity than you can avoid moving forward in time. And the singularity itself? That's a place where general relativity breaks down completely. Infinite density, infinite curvature. The equations give meaningless infinities. Most physicists think this means we need quantum gravity, a theory that merges quantum mechanics and general relativity to understand what really happens at the center of a black hole. Some theories suggest the singularity isn't a point, but a gateway, a wormhole to another region of space-time or even another universe. Others suggest it's a firewall of high-energy particles that destroys anything approaching it. Still others suggest that quantum effects prevent the singularity from forming at all, creating instead a highly dense but finite core. We don't know. And here's the terrible truth. We might never know, because anything that crosses an event horizon can never send information back out. The interior of a black hole is literally beyond the light barrier in the most absolute sense possible. It's not just distant. It's causally disconnected from the rest of the universe. It exists, but in a way that's fundamentally unknowable to anyone outside. Black holes are regions of spacetime that exist beyond our ability to observe or interact with. They're pockets of reality sealed off by the speed limit itself, and they're everywhere. Our galaxy has millions of them. The universe has trillions. A huge fraction of reality is locked behind event horizons, forever beyond reach. What exists beyond the speed of light? In the case of black holes, the answer is entire regions of spacetime, potentially more spacetime than exists in the observable universe, locked away where the light barrier is an absolute wall. Let me ask you something that's going to sound weird. Are you the same person you were 10 years ago? You probably said yes, but think about it. Every atom in your body has been replaced multiple times since then. Your memories have changed. Some have faded, others have been reconstructed, maybe even altered. Your beliefs, your personality, your preferences have all evolved. The pattern is similar, but the physical substance is completely different. Now imagine that black holes work the same way. The information that falls in gets scrambled, encoded on the horizon, eventually radiated back out as Hawking radiation over trillions of years. Is the information that comes out the same as what went in? Or has it been so transformed that the identity is lost? This isn't just about physics. It's about the nature of identity, of continuity, of what it means for something to persist over time. And it connects to our discussion of light speed, because causality, the flow of cause and effect at speeds limited by light, is what creates continuity in the first place. If you're still here, still engaged, please like this video. Share it with someone who loves questioning reality. And comment, What aspect of black holes do you find most unsettling? The information paradox? The fact that time and space swap roles? The existence of a singularity where physics breaks down? We're entering the final stretch now, and I promise the way all of this comes together is going to reframe everything we've discussed. I've been dancing around something for this entire video, and now it's time to address it directly. What role does consciousness play in all of this? We've talked about how quantum wave functions collapse when observed. We've discussed how different observers see different things when someone falls into a black hole. We've explored how the observable universe is defined by what you can see, which depends on your position and motion. Throughout all of this, there's been an implicit question. Does consciousness somehow matter to physics? This is controversial. Most physicists are uncomfortable with the idea that consciousness plays any special role. They prefer to think of observation as just any physical interaction, not necessarily involving a conscious mind. When a photon hits a detector, the detector observes it in the relevant sense. No consciousness required. But some interpretations of quantum mechanics give consciousness a more central role. The von Neumann-Wigner interpretation, developed in the 1930s by John von Neumann and Eugene Wigner, suggests that consciousness is what collapses the wave function. Until a conscious observer looks, the system remains in superposition. This raises the question, what counts as a conscious observer? Does a dog count? An insect? A bacterium? A sophisticated AI? Most physicists find this unsatisfying because it makes consciousness a fundamental part of physics without explaining what consciousness is or how it does this collapsing. But the question won't go away. Some version of it appears in almost every interpretation of quantum mechanics. In the many worlds interpretation, consciousness is what determines which branch of reality you experience. The wave function never collapses, but your consciousness follows one particular thread through the branching multiverse. Why that thread and not another? We don't know. But your subjective experience, your conscious awareness, somehow selects one reality out of the infinite superposition. Here's where this connects to our topic. If consciousness is involved in determining what's real for you, then what exists beyond the speed of light depends, in some sense, on you. Not just on your position in space, but on your conscious experience, on what you observe, and what you can observe. Think about it. The cosmic event horizon defines the boundary of what you can causally interact with. But what does you mean in this context? Your physical body? Your conscious experience? Your information processing capabilities? If you had a more advanced brain, could you process information in ways that effectively see farther? If you lived longer, would your cosmological horizon expand as more light had time to reach you? In what sense is the boundary of the observable universe an objective fact versus a subjective limitation? This becomes even more interesting when we consider artificial intelligence. If we create an AI vastly more intelligent than humans, with greater information processing capacity, does it experience a different observable universe? Can it extract information from quantum correlations that we can't? Does its consciousness, if it has consciousness, interact with reality in different ways? Some physicists and philosophers have proposed that consciousness itself might be a quantum phenomenon, that the weird features of quantum mechanics, like superposition and entanglement, might be essential to how consciousness works. Roger Penrose and Stuart Hameroff have developed a theory called orchestrated objective reduction, or OR, which suggests that consciousness arises from quantum processes in microtubules inside neurons. This is extremely controversial. Most neuroscientists think consciousness is a classical phenomenon, the result of complex neural networks, but not requiring any special quantum effects. The brain is warm and wet, conditions that usually destroy quantum coherence. But we don't actually know for sure. We don't have a complete theory of consciousness. If consciousness is quantum, in your conscious experience might be connected to the rest of the universe in ways we don't understand. Quantum entanglement, which we know operates instantaneously across space, might link conscious observers in subtle ways. Not telepathy in the science fiction sense, but perhaps a deeper connection through the universal quantum state. This brings us to a truly wild idea proposed by some physicists, the participatory universe. This concept, developed by John Archibald Wheeler in the 1970s, suggests that the universe requires observers to exist. Not that observers create the universe through observation, but that the universe and observers co-create each other in an ongoing process. Observation brings quantum possibilities into definite existence, and definite existence enables observers in a self-consistent loop. Wheeler illustrated this with what he called the delayed choice experiment. You can do a quantum experiment where you decide how to measure a photon after it's already passed through the apparatus. Your choice in the present seems to retroactively determine what the photon did in the past. It's as if your observation reaches backward in time to solidify what happened. This isn't time travel in the usual sense, but it shows that the relationship between observation and reality is far stranger than common sense suggests. The past isn't fully determined until observed. Reality is, in some sense, a collaboration between the physical world and conscious observers. If this is true, then what exists beyond the speed of light might depend on whether there are observers there to observe it. A galaxy beyond our cosmic horizon doesn't interact with us, but does it still exist in the same sense as galaxies we can see? Or does it exist in some kind of quantum limbo, a superposition of possibilities, until some observer somewhere observes it? These are deep waters, and I'm not claiming to have answers. No one does. But the questions themselves are profound. They force us to think carefully about the relationship between consciousness, observation, causality, and reality. Here's what I want you to take away. The speed of light doesn't just limit physical travel. It limits causal influence, the ability to affect what happens somewhere else. And causality is intimately connected to observation, to information, to knowledge. The light barrier is as much an epistemological boundary as a physical one. It defines not just what you can reach, but what you can know. And if consciousness plays any special role in physics, which is still an open question, then the light barrier might also define something about the scope of conscious experience itself. Your consciousness exists in a local bubble, able to have direct causal relationships only with a limited region of spacetime. Everything else is beyond your reach, beyond your ability to influence, beyond the speed of light. But that local bubble contains everything you'll ever experience, everyone you'll ever interact with, every moment you'll ever have. The limitation creates the meaning. Without boundaries, without the light speed horizon, experience itself might not be possible in any coherent sense. You are a consciousness existing in a bounded region of spacetime, able to observe and interact with a tiny fraction of reality, forever separated from the vast majority of what exists. But that tiny fraction is your universe, your reality, and it's real and meaningful precisely because it's bounded, because it's yours. Let's bring this back down to earth, literally, and talk about practical implications. What difference does any of this make to your actual life or to the future of technology? More than you might think. Understanding the speed of light and its implications has driven some of the most important technologies of the past century and will drive even more in the future. GPS satellites are a perfect example. Your phone's GPS works by receiving signals from satellites orbiting Earth at about 20,000 kilometers altitude. Those satellites are moving at about 14,000 kilometers per hour relative to Earth's surface. At those speeds, special relativity causes time dilation. The satellite clocks run slower than clocks on the ground by about 7 microseconds per day. But there's also general relativity to consider. The satellites are higher in Earth's gravitational field, where gravity is slightly weaker. This causes their clocks to run faster by about 45 microseconds per day. The net effect is that satellite clocks run about 38 microseconds per day faster than Earth clocks. This might not sound like much, but GPS works by measuring the time it takes signals to travel from satellites to your phone. Light travels about 300 meters per microsecond. If we didn't correct for relativistic time dilation, GPS would accumulate errors of about 10 kilometers per day. Within a week, GPS would be completely useless. Every time you use GPS to navigate, to find a restaurant, to order a rideshare, you're relying on Einstein's theories of relativity. You're using technology that requires understanding how time behaves near the speed of light and in gravitational fields. The physics we've been discussing isn't abstract. It's running in your pocket right now. Future technologies will push this even further. One of the most exciting areas is quantum communication. We talked earlier about how quantum entanglement creates instantaneous correlations, but can't be used to send information faster than light. But it can be used for something almost as good, perfectly secure communication. In quantum key distribution, you use entangled photons to create a shared encryption key. Any attempt to intercept or measure the photons breaks the entanglement, alerting you that someone is eavesdropping. This allows provably secure communication, guaranteed by the laws of quantum mechanics. China launched a quantum communication satellite called MIJIS in 2016, demonstrating quantum key distribution between ground stations thousands of kilometers apart. Several countries are now developing quantum communication networks. This technology will become increasingly important as quantum computers become powerful enough to break traditional encryption. Speaking of quantum computers, there's another technology that directly exploits the weird features of quantum mechanics. A quantum computer uses qubits that can be in superpositions of 0 and 1 simultaneously. This allows quantum computers to explore many possibilities in parallel, potentially solving certain problems exponentially faster than classical computers. Google claimed quantum supremacy in 2019 when their Sycamore processor performed a specific calculation in 200 seconds that would take a classical supercomputer about 10,000 years. IBM and others disputed the details, but the general point stands. Quantum computers are becoming real, practical technologies, and they're directly connected to our discussion of what exists beyond the speed of light. Quantum computers exploit superposition and entanglement, the same phenomena that create faster-than-light correlations and parallel quantum worlds. Every quantum computation is, in a sense, exploring all possible solutions simultaneously across the many worlds multiverse. You're harnessing the computational power of parallel universes. That sounds like science fiction, but it's how some physicists genuinely understand what quantum computers are doing. David Deutsch, one of the pioneers of quantum computing, explicitly describes it this way. When a quantum computer factors a large number, it's distributing the calculation across exponentially many parallel versions of itself in different quantum branches, then bringing the results together through quantum interference. Whether or not you accept the many worlds interpretation, the practical reality is that quantum computers work, and they work by exploiting phenomena that seem to violate classical causality and locality. Now let's talk about something more speculative. If we ever develop technology to create wormholes or warp drives, what would that mean? Imagine you have a stable wormhole connecting Earth to a planet orbiting Proxima Centauri, 4.24 light-years away. You could step through and arrive instantly. But remember, instant for whom? From Earth's reference frame, you arrive at Proxima Centauri before any light signal sent from Earth at the same time you left. You've traveled faster than light. But here's the thing. If you turn around and look back at Earth through the wormhole, you see Earth as it was when you left. Light still has to travel from Earth to Proxima Centauri the long way, taking 4.24 years. So you could, in principle, watch yourself leave Earth while standing on Proxima Centauri. This creates all sorts of potential paradoxes, which is why many physicists think exotic structures like traversable wormholes probably can't exist, or if they do, there must be some mechanism that prevents them from causing logical contradictions. But the theoretical work continues. In 2017, a team of physicists published a paper showing that entanglement and wormholes might be fundamentally related. The E=EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013, suggests that quantum entanglement creates tiny wormholes in spacetime. Two entangled particles are connected by a microscopic Einstein-Rosen bridge. If true, this would mean that quantum mechanics and general relativity, which currently seem incompatible, are actually describing the same phenomenon from different perspectives. Entanglement is the quantum mechanical description, and wormholes are the gravitational description of the same underlying reality. This hasn't been proven, but if it's correct, it opens up fascinating possibilities. Maybe we could manipulate entanglement to create macroscopic wormholes. Maybe we could use quantum effects to engineer space-time geometry directly. Maybe the path to faster-than-light travel isn't through brute force propulsion, but through understanding the deep connections between quantum mechanics and gravity. NASA's Breakthrough Propulsion Physics project, which ran from 1996 to 2002, investigated these kinds of possibilities. While the project was officially closed due to budget constraints, research continues in various forms. The Tau Zero Foundation, founded by physicist Mark Meelis, who led the NASA project, continues to explore revolutionary propulsion concepts. One of the most promising areas is the study of the quantum vacuum. Empty space isn't actually empty. It's filled with quantum fields fluctuating with virtual particles, constantly popping in and out of existence. The Casimir effect, which I mentioned earlier, shows that this vacuum energy is real and can be manipulated. Some theorists have proposed that if we could create regions of negative vacuum energy density on a large scale, we might be able to construct Alcubierre-style warp drives or stabilize wormholes. Harold White's work and NASA EagleWorks suggested that by oscillating electromagnetic fields in specific geometric configurations, you might be able to create tiny perturbations in spacetime. The measurements were controversial and haven't been independently replicated, but the theoretical framework is sound. If you can manipulate vacuum energy, you can in principle manipulate spacetime geometry. And if you can do that, you can create shortcuts through space that effectively allow faster-than-light travel without violating relativity. But let's be realistic. We're probably centuries away from anything like this becoming practical. The energy requirements are staggering. The engineering challenges are immense. We don't even have a complete theory of quantum gravity yet, so we're working partially in the dark. Still, the fact that these things are theoretically possible, that they don't violate the known laws of physics, means they're not science fiction. They're extremely advanced engineering. And human history has shown repeatedly that what seems impossibly advanced to one generation becomes routine to the next. In 1900, no one could have imagined GPS satellites accounting for relativistic time dilation. In 1950, no one could have imagined quantum computers harnessing parallel quantum worlds. What seems impossible today might be commonplace in 2125 or 2225. Here's what's practical right now. Understanding the speed of light and its implications helps us develop better technologies, more accurate timekeeping, better navigation systems, quantum communication networks, quantum computers, more precise scientific instruments, better astronomical observations. Every time we push against the light barrier, every time we try to measure things more precisely or communicate more effectively across distance, we learn something new about the fundamental structure of reality. And that knowledge feeds back into technology, which enables new experiments, which reveal new phenomena in an ongoing cycle of discovery and application. The speed of light isn't just a physical constraint. It's a target, a challenge, a boundary that pushes us to be more creative, to think more carefully, to develop better mathematics and better theories. Racing toward the light barrier has driven some of humanity's greatest intellectual achievements. And who knows? Maybe one day, centuries from now, a future human or post-human intelligence will find a way to manipulate spacetime itself, to create controlled wormholes or warp bubbles to access the regions beyond our current cosmic horizon. Maybe they'll develop technologies we literally can't imagine, using principles of physics we haven't discovered yet. Or maybe the light barrier will remain absolute, an eternal horizon that can never be crossed. Even if that's true, it doesn't diminish the profound beauty of what we can achieve within our light speed bubble. Sometimes limitations inspire greatness. Let's think about the far future. Trillions of years from now, what happens beyond the speed of light becomes a question about cosmic destiny itself. Right now, the universe is about 13.8 billion years old. That seems incredibly ancient from a human perspective, but cosmically speaking, it's young. The universe is going to exist for an incomprehensibly longer time, and what happens beyond our cosmic horizon will determine its ultimate fate. The current leading model is called the lambda CDM model, where lambda represents dark energy and CDM stands for cold dark matter. According to this model, dark energy is causing the expansion of the universe to accelerate. Distant galaxies are receding from us faster and faster, and this acceleration will continue indefinitely. In this scenario, the cosmic event horizon will continue to shrink. More and more galaxies will slip beyond our ability to ever reach or observe. Eventually, in about 150 billion years, as calculated by Lawrence Krauss, every galaxy outside our local group will have disappeared beyond the horizon. The local group, consisting of the Milky Way, Andromeda, and about 50 smaller galaxies, is gravitationally bound. They're pulling on each other strongly enough that cosmic expansion can't tear them apart. In about 4 billion years, the Milky Way and Andromeda will collide and merge into a larger galaxy, sometimes called Milkomeda. But everything else will be gone. Future civilizations living in Milkomeda, looking up at the sky, will see a dark, empty universe with no other galaxies visible. They'll have no evidence of cosmic expansion, no cosmic microwave background radiation. It will have redshifted to undetectable wavelengths. No ability to discover the Big Bang or the vast cosmic structure we can see today. Unless they find historical records or artifacts from civilizations that existed earlier, they'll think Milkomeda is the entire universe. They'll be cosmologically isolated, trapped in a bubble with no way to learn about the larger reality beyond. But the story doesn't end there. As the universe continues to expand and cool, stars will eventually stop forming. The last star will form perhaps 100 trillion years from now. After that, the existing stars will gradually burn out. Brown dwarfs will cool to black dwarfs. Planets will be ejected from their orbits or fall into stellar remnants. In YY years, that's 1 followed by 40 zeros, protons might decay if certain theories are correct. All ordinary matter would gradually disintegrate into radiation and subatomic particles. Even if protons are stable, black holes will eventually evaporate through Hawking radiation. The largest black holes, supermassive black holes billions of times the mass of the Sun, will take about 10,100 years to evaporate. That's a 1 followed by 100 zeros, a googol of years. By comparison, the current age of the universe is only about 1,010 years. After the black holes evaporate, the universe will enter what's called the dark era. Only cold, dispersed subatomic particles and photons will remain, spread across an expanding universe. The temperature will asymptotically approach absolute zero. Nothing interesting will happen, ever, for eternity. This is sometimes called heat death, the idea that the universe will eventually reach maximum entropy, a state of total disorder where no energy differentials exist and therefore no work can be done. no life, no thought, no complexity of any kind. Just a cold, dark, empty expanding space for infinity. This sounds depressing, but here's a fascinating perspective. Physicist Freeman Dyson proposed that even in this far future, life might be possible in a very different form. If intelligence can transfer itself to substrates that operate at lower and lower temperatures, and if information processing can be slowed down appropriately, civilizations might survive indefinitely by going into longer and longer periods of hibernation. Think of it like this. As the universe cools, you need less energy to perform computations. If you're willing to think very, very slowly, you can make a finite amount of energy last forever. Dyson calculated that by having thoughts progressively farther apart in time, a civilization could have an infinite number of thoughts using only finite energy. Of course, this assumes protons don't decay and that dark energy doesn't evolve in unexpected ways. But it's a beautiful idea that even in a dying universe, consciousness might persist forever, thinking infinitely many thoughts across infinite time, even as the material universe becomes more and more sparse and cold.